Hi, this is Rob Bolaños. Welcome to the analysis and design of a flyback converter. This is video 27, and I'm going to show how to derive the small signal model and then how to use MathCAD. And then I'm going to compare it with Spice simulations. So we're going to compare both of them. Okay, see how accurate they are. Okay, and this is the small signal model. And I'm using Jack's model. If you're not familiar with this, there is a playlist called Compensation, and on that one I explain Jack's model. I go through the how you can implement it in Spice. So I'm using this model basically, and the main point of Jack's is that he uses the divider. Here's a divider. Which is basically R1 and R2. And then this is your error app. And this would be used also in your switching model. So this is kind of this is an average model. Okay. And then past this point, this pin is the output of the error ramp. This is often called the compensation pin. Okay. So after the compensation pin, he goes directly to the output. So this is the output. And then that is fed back to the divider. So here is Jack's model or device. He uses a voltage control current source. So it's a voltage control current source to model current mode. And if you're using voltage mode, PWM, then it would be a voltage control voltage source. Okay. So anyway, we're not using that. We're going to be using this one, the control mode. It's a voltage control current mode, and that's what we're going to be using. Okay. So when you're doing the loop analysis, what you're doing is you're putting a external source. In this case, you inject a signal, and here is your signal. That signal, let's start here. We'll call this as the input. The little wiggle gets divided down. Okay. And then it goes to the error amp, and at low frequency it gets amplification. Okay, and then it goes through this modulator, and I'm going to call this the PWM. Okay, and then that wiggle comes out through the feedback, and then it gets compared. So you should get a sinusoidal wave at this note, and then a sinusoidal at this note. And when you do a simulation, you're comparing the amplitude, the magnitude, and the phase. Okay. So when you do that, you basically, it's going through this loop. It's going through here, and back, and so forth. So that's the loop that we're going to derive. Okay. So we have to start somewhere, and we're going to go ahead and start with the output filter. And the output filter is basically composed of this resistor, that's the ESR. That one is this one. Your C out, which is your output in capacitor, and then your load. Okay, and we're going to be using the S domain, the plus domain, which is 2 pi f imaginary j. Okay, so to derive the equation, since we're gonna be using impedances, the S domain works out very well. Okay, so in this case, you have to recognize that this circuit and this circuit are in parallel to each other. So you can make your first equation, you can say that RL is in parallel with the series combination of R ESR and C out. So that's your first equation. Okay. Then since this are in series and we're talking about resistance, hopefully you'll remember that when you have resistors, and impedance is a form of resistors, you would have this form to calculate the parallel combination. You would do R1, R2, R1 plus R2. So this is the formula to combine two resistors. Okay, so we use the same formula. Okay, so you notice this would be R1, and you can think this as R2. So here is R1, and if you notice you're multiplying, here is R2, and then here's R1 plus R2. Okay, so you have this now. Okay, so let's go through the mathematics, and if you're bored with the mathematics, you can skip down below, but I'm going to try and show a little bit of rigor. It's been a while since I've done some of this. Okay, so I believe I bring the equation here. Okay, and what I did is I distribute the R's, yes, the RL, I distribute, multiply it across, and I believe I didn't do anything to the bottom. Yes, stayed the same. So up to here, so basically I multiplied. So now, since we have this term right here, let me see, where's my, okay, since I have a denominator here, I'll look for the common denominator. So that's what I'm doing here. I set this to SC and so forth, and I come out with the common denominator, so I come up with this equation. Okay. Okay. So then, once I have this equation, I bring it here. And what I want to do here is I want to divide this term and this term by itself, and therefore this comes down here, so you end up with this equation. Okay, hopefully you can follow that. Okay, then the RL's cancel, should be ESR. Okay, so now here you're showing this is the 0. Here's a pole. Okay. Okay, so now let's refine it a little bit. Now, interesting, the 0 is a function of, let's go on this right here. So you notice there's a 0, which is a function of the output capacitance and the ESR resistor. Okay. Now, if you notice down here on the pole, you also have the ESR, but now RL is also involved. So basically, it's a combination of RL and ESR. Okay, and if you remember, for the pole, I always say that it's a function of the load resistor. I never mentioned anything about the ESR. However, ESR is typically much smaller, and RL is bigger typically. And if R ESR, you want it small because that determines your voltage ripple. Okay, so you want this to be as small as possible. So if that's the case, then this goes to 0, or you can neglect it, so you end up with this equation. So this is the equation for the output filter. Okay. Now this will give you a gain. And gain. So I can be able to plot it properly on one unity. So what I want to do is I bring out these coefficient, the ESR, and I bring it out to the front. So basically this will give me a unity gain. Okay, so this is the equation that we're going to be using. Okay, so we're that far. Okay, so now we have the transfer function of this impedance. Okay, so now we're going to find out what is the gain of the PWM. Okay, and typically to show that, see this coefficient, that coefficient is calculated by this voltage. Basically, it's whatever the current is going out through here and whatever this voltage is. But we're going to simplify it. What we want to do is we're going to set this to 3 volts, because typically that's what the voltage coming out of the comp pin will be about 3 volts. So in this example, I'm using this 12 volts. So the gain from here to here from the input of the PWM is 3 volts, and the output of the PWM is 12 volts. So the gain is 4 for the PWM. So that's what this equation is. Okay. So the gain of the PWM will be the voltage output divided by 3 volts. Okay. And remember, this 3 volts is the voltage at the comp pin. Comp pin is the compensation pin of the PWM. Or actually, I can say, let's say error amp. Okay. Okay. So now we're going to derive the equation of the error amp. Okay. And instead of writing C integrator for this one and C roll off, I went ahead and just abbreviate it just to make the derivation a little easier. Okay, so if you follow this, the signal is coming in through here and the signal comes out through here. So the transfer function, and if you want take a look, if you do the Thevenin of this, the Thevenin is R1 and R2 in parallel. So basically you have this here. Okay. And now this is your voltage reference. So and when you do AC signal analysis, this is shorted. So you can think of this as this. Okay, so these are equivalent. Okay, and if you notice, then you can say you should know already that the gain of an inverting is going to be your R feedback, whatever is in the feedback, divided whatever is in the input, or in this case it's going to be RTH, or this basically. So this part is in the numerator, and this is in the denominator. Okay, so now that I have that, then we can write the mathematical functions. Okay, so this is going to be Z1. This is the impedance of this here, and we can say that it's R1 in parallel with R2. So here you have the equation. So then we can formally say that Z1, which is this part, or this part, is this function. And then Z2, if you do the circuit analysis, you can see that C2 is in parallel with the series combination of the RF plus C1, the integrator. So this is where we can say that C2, this is C2, is in parallel with this combination, which is right here. So then when you do the math, you end up with this equation. And instead of multiplying that out, we're going to go ahead and leave it like this. Okay. And we'll use MathCAD to do the math. Okay. Oh, and here, I showed it right here. That's that here. Basically the gain is the inverting. Okay. Okay. Now you can go ahead and leave this part out if you wish, but you have to recognize this is the equation of the OpAmp. Let me see right here. Okay, and typically you would not look at this term. Typically the gain would be Z out, no, Z2 divided by Z in. That would be the gain of the error amp. However, if you have an op-amp has finite gain, so you can take into account the effects of the gain and the bandwidth, and you do it with this equation, okay, and this equation. So basically this AO is the gain of the op-amp and also the bandwidth. Okay, now for those who have taken circuit theory, when you plot the gain of an op-amp, the gain is usually very high. Okay, and then it has a low corner frequency where it starts dropping, and typically this would be your gain, open loop gain of the op-amp, and then this where it starts dropping, that's the bandwidth. Okay, and this typically would be maybe 105. That's what I'm using, 105 dB, and I'm using a bandwidth of 5 Hertz. Okay, and then where it crosses 0, that's usually called unity gain. Okay, so basically what I'm trying to do is I'm trying to model this, the effects of the op-amp, because if you have an op-amp that has a gain of 40, which is only 100, then it's going to have a big effect on this. So basically what I want to say is this A sub O is infinite. meaning that this is very, very high, then this term goes to 0. And this simplifies to when the gain is infinite. However, when it's not infinite, then you have to take that into account. So this, I'm representing it because it does affect the gain of the total loop. Okay, so you'll see what I mean. Anyway, and to model that, this is where I express the gain. Here is the you put the dB. So in this case, I would put 105 dB here, and then the bandwidth, that would be 5 hertz. Okay, hopefully that makes sense. And then the last is a divider network. So this is the equation. Okay, so now you have all of these equations. This equation. We're going to have this equation. Let me clean it up. See if I can clean this up. Okay. Let's see what else. I have Z2, Z3. Okay. So basically, let's go down here. So basically, we have all the equations that we need to do a loop plot or a Bode plot. So this, okay, this is the output filter. Here is the PWM. Okay. Here's the error amp. Okay. And then this is this equation, this A, that is this equation. 10. Hang on. See, what is it? S plus, yeah. Okay, so that's where that goes. And then this is the divider. Okay, so now what do we do now? So now we're going to go ahead and use MathCAD. And then we're going to compare it with Spice. Okay. So okay. So before we do any scripting, be sure you copy this. On that, this is pretty self-explanatory. So it gives you the start frequency, end frequency, and the points. So it calculates and sets up your Bode plot. Okay, so be sure you copy this. Not sure if it. Let me go ahead and zoom in. Okay. If not, can't copy this, you can ask for the example PDF or a MathCAD script. I can send it to you. Okay. So you need to copy this first. Okay. So let's go ahead and continue. Now here is where let me go ahead and close this. computer's been having some problems. I need a new computer. Slowing down a little bit. Anyway, so here I put the values that I had already calculated or I have in my SPICE simulation. These values are coming from this here. Okay. So here are my values. Here is my output capacitor, my load ESR. These are my compensation components. Okay, here's my integrated resistor, integrated cap, my roll-off cap, and then my divider. Okay, here's the gain of the output filter, and you define it. Make sure that you include this term because it's in terms of in the S domain. Okay, here is the equation for the PWM. Here is the equation of the error amp. Here I define the impedance of Z1. Okay. Here is the impedance of Z2. Okay. So then this equation defines the transfer function. Here is negative Z2 divided by Z1, and then this term here is the OpAmp gain defined as well in terms of S. Okay, and then this is where I define the properties of the OpAmp gain. So I'm saying that the gain is going to be 105 dBs. Okay, and I'm going to define it that the bandwidth is 5 Hertz. So here I defined it, and then again it's expressed here. Okay, so that's the property of. Okay, so then this would be the divider. Okay, so here is the equation of the divider. Okay, so now I can put everything all together. So I have 1, 2, 3, 4 terms, which is the same 1, 2, 3, 4 terms. So now I can do a loop analysis. All I do is I define this 20 log, and it's the magnitude of loop equation. And then here, to get it to function, you want to set up a subcircuit or a subscript. And basically, it's going to go through. That's what makes it plot. And then you plot over frequency F sub 1 I. Okay, these are already set up by the first lines of the MathCAD. Okay, so now you can see that this is the magnitude of the loop, and this is the phase. So now you should be able to come over here and see where does it cross over. And it crosses about, let me see, it goes to 0. That's close. That's close. So it has a bandwidth or a crossover of 6,395, and then you can come up here, and the phase is 53.9. Okay, so let's compare this. Let's go ahead and do a body plot of this. Okay. Okay. Let's see if I can this out here. And if you notice, okay, it looks pretty similar. Okay. Yes. Okay. So here I said that there's a 53. Okay, so we go to 0 here. And here the loop is 49, 53, and it's crossing over at 6,000, I believe. So that's very pretty close to each other. Okay, it's crossing at 0. Yeah, 6,000, and this is 63. Okay, so they even have the same hump right here. That hump is here at 0, and then you have the 0, and then yes, here's the 0 where it pulls up. There's a pole, 0, and so forth. So you notice it looks good. Now typically I don't plot anything above 100 or 1 meg. This is all parasitics, so I like to keep this less than 1. Okay, so I can go ahead and set this to 1 as well. See what happened there. Okay, so now it looks very similar. Okay, so anyway, so that's what I wanted to show you, that you can now plot this mathematically, but not only can you plot the output, you can also plot individual parameters. Like for example, if you wanted to plot excuse me, the output filter, here's the brown one. Okay, you can show that as well. Let's go ahead and go to 120. Okay, so you can see the effects of the output filter. So here's the output filter, here's the pole, and then you have the 0. Okay, plus you can also show it here because this is getting a little copy. I'll go ahead and put it over here. Maybe do the comma paste. Okay, so now you can see the error amp. This is the error amp, the black one. And remember, when we do the loop compensation, we try to match this 0 with this pole. So we match it, and there should be a 0 here, but I think because of the gain of the OpAmp, it does not match. See, here's the pole, here's the 0. The 0 should be over here on the error amp, but the OpAmp doesn't have enough bandwidth or gain. So let's see. So let me go ahead and see if I can take this off the face. So that would be this one. That way it doesn't disturb us. Okay. There. So this is what I'm trying to get at. That this pole is cancelled by this 0. And then it looks like there's a 0 over here when it should be over here. Okay. So let's up the gain and see what happens. Okay. Let's say that the gain is 120. Okay, so let's see, does it do anything? If you notice, it looks like it went a little bit higher. Okay, let's say it goes up even higher, 160. And if you notice, now they're matching. You see that? Okay. Okay, let me see if I can show both. I wonder if I can copy this. Let me see if I can copy this and paste it on this side. Will it work? No, it has to be below. Okay. I can't do it. Okay. But okay, I think you can see the effects. Okay. Okay, I think I'll know what I do. I'll take this off. Bring this up. And this is the reason that I put the parameters due to the OpAmp, because the OpAmp has a big influence. Okay. Okay. So basically, the gain affects this pole. So let me go back. Let's make it really, really bad. Let's make it 60. You notice that it doesn't even have enough gain. So let's go 80. See, so the pole's here, and the zero's here, and the pole's here. Okay, let's go 100. So now it's over here. Okay, so if I go another decade of gain, this should come up. So let's go. Okay, notice now it's creeping up. It's gonna match close to this. Okay, so now I go another, let's say go to 60. Now if you notice, basically catching. Okay, so let's go to 200. Yeah, that's about it. So at about 150, 160 is probably where you have enough gain to compensate for that. Okay. So anyway, this is what I wanted to show you. I think this is pretty neat. It's pretty neat that you're able to plot all of these, and you can also show it in multiple. You can show all. You can show the loop, the error, and the output filter, and so forth. Anyway, if you have you found this educational, please like it, share, and subscribe. If you have any questions, you can email